the next talk will be given by Diana Kai from University of Chicago, who will present joint work with Trevor Campbell and Tamara Broderick on edge-exchangeable graphs, sparsity.
Great. Can everyone hear me? Okay, so I'm going to be talking about edge-exchangeable graphs and how we can use these to get sparsity and power laws. This is joint work with Trevor Campbell and Tamara Broderick at MIT. And you may have gone to Harry Crane's great talk on Monday, also on edge exchangeability. This is concurrent work, so you'll see some similarities and some differences, and I hope that this will convince you as an audience that this is an exciting problem. So in the real world, we often observe individuals and their interactions, and so we can model this as a network. Some examples might be friendships on something like Facebook, where these friendships represent the edges between users. We might also observe some graph with multiplicities, such as an email communication network, where messages are being sent back and forth between users. Similarly, in something like a co-authorship network, interactions represent papers co-authored by two people. And so this type of interaction structure occurs naturally in many applications. And what we as a community are interested in doing is putting some distribution on these graphs and building a probabilistic model of these graphs. And then what we want to do is, given these observed networks, we want to infer their parameters. And so some example of this might be if we wanted to infer some latent community structure in the network. And so there have been a lot of popular graph models developed for this purpose. And one example is the stochastic block model, and it has very many variants as well. The problem is that many of these traditional graph models, in fact, this class of exchangeable graph models, is that they produce dense graphs. And this means that there are too many edges in the graph. I'll define what this means more formally later, but you can think of this sort of as like a complete graph where every vertex is connected to every other vertex in the graph. And so you might consider the example of Facebook again, where it might be absurd to make that assumption because you wouldn't expect any user in the network to be connected to everyone else in the network. And so in the real world networks, we assume some sort of sparsity in that there aren't that many edges in between the users. So what we propose is a new framework that allows us to get sparse graphs in power laws. Now I'm going to step back from graphs for a minute. I'm just going to talk about regular random variables, or suppose we have this data sequence, x1 and x2, etc. And we say that this sequence is exchangeable if we look at any finite collection of these data points, and if we permute their indices, it won't change the distribution of our data. And so we can imagine if we have some distribution, we can then sample a parameter, and then given this parameter, we can sample an exchangeable sequence, conditionally IID given the parameter. So what Di-Finetti's theorem tells us is the converse of this. In fact, for any exchangeable sequence, there exists such a model or such a distribution that characterizes the distribution of this sequence. And so this is also known as a Di-Finetti mixing measure, and this is going to come up again and again in this talk for different types of random structures, such as graphs. And so in Di-Finetti's theorem, we have a sequence of data, and so now I want to think about a sequence of graphs. And so you might think that in the real world, I only observe one graph, so where is my sequence? And you can actually think of something like this G here being built up as a sequence of graphs, where at every step in the sequence, we're going to be adding vertices and edges to the sequence. So here's an example. We might start out with a single vertex, and then in the second step, we could add a vertex and add an edge and two vertices, and maybe in step 4, we added 3 more edges, and we get something that looks like this G. And so we're going to assume in this talk that in this graph sequence, we can only add edges and vertices, and we can't delete anything in our sequence. And so what we are interested in is the behavior of the sequence as it goes on and on. In particular, we can define what it means for a graph sequence to be dense. That is, as the number of vertices goes to infinity, the number of edges grows quadratically in the number of vertices. By contrast, we can think about sparse graph sequences, where now the number of edges will grow subquadratically in the number of vertices. But this is sort of one of the weakest definitions of sparsity in a graph sequence. In practice, we might be interested in something more like polynomial growth, where the exponent is strictly between 1 and 2. And so in this case, I'm going to refer to this as a sparse power law or subquadratic power law. And so this also has a power law between the relationship of the vertices and the edges. So now that I've introduced graph sequences, I'm going to talk about the traditional notion of exchangeability in graphs. And so this is how people thought about modeling graphs. Okay, so we're going to consider the following type of sequence. So in every step of the sequence, we're going to bring in one new vertex, and that vertex is going to instantiate any edges with existing vertices in the graph. And then for convenience, I'm also going to label these vertices by the step in which they entered the graph. So suppose this first vertex, we give it a label 1 because it came in the first step of the sequence. And then in step 2, vertex 2 comes in and joins with vertex 1. And maybe in step 3, vertex 3 comes in but doesn't join with 1 or 2. And so further in the sequence, we won't see any more edges between 3 and 1 and 3 and 2. And so any other edge that vertex 3 will participate in has to come from a future vertex entering this sequence. And so now 4 does that and brings an edge with 3, 2, and 1. And so what we're going to do is we're going to put a distribution on this graph. And we say that this is exchangeable if this distribution is invariant under permutations of the order of the vertices. So here I have on the left this original sequence that I showed up here. And then we can see that the vertex that came in step 1 is now coming in at step 2. So to differentiate this from our idea of edge exchangeability, I'm going to refer to this as vertex exchangeability. So now I'm going to tell you how we can generate a vertex exchangeable graph. And so first I'm going to talk about graphons. And so a graphon is a symmetric measurable function from the unit square to the unit interval. And here's an example. This picture represents the unit square, and the color represents a value between 0 and 1. And so here I've just plotted a specific function given right here. But in general, we're actually interested in the case where W, or this graphon, is random, because we want to build these Bayesian generative models, which amounts to putting priors on these functions. So back to this sort of generative process. Because this is a symmetric function, I'm going to focus my attention on only the top half of this triangle. And so then what we're going to do is we're going to sample uniformly from these IID uniform random variables from the unit interval, and these are going to correspond to vertices. And then we're going to look at the probability of the intersection at this function and flip a coin for an edge with that probability. So suppose the first uniform random variable lands here. This corresponds to the first vertex. And then if the second one lands here, we're going to look at the intersection and flip a coin with this probability. And so this gives the probability of an edge between vertex 1 and vertex 2. So maybe that comes up as a head, and we get an edge. Maybe the third uniform random variable lands here, and so once again, we'll look at the intersection between 1 and 3, and suppose this gets a head, and we get an edge, and then the intersection between 3 and 2, and maybe we don't get an edge. And so this produces a vertex exchangeable graph. If we were to permute any two vertices, what this amounts to is permuting two IID uniform random variables, and so permuting these vertices isn't going to change the distribution of our graph. And so in fact, this graphon gives us essentially everything, in that Aldous and Hoover showed that any vertex exchangeable graph has such a graphon representation. And so here are some examples of realizations of random graphons corresponding to some popular graph models, such as the Erdős-Renyi graph, stochastic block model, and the infinite relational model. So a consequence of this is that if we were to look at the expected number of edges in the graph at step n, this corresponds to this expectation of this n choose 2 term, which is the number of possible edges between n vertices. And then we're looking at this integral over our random graphon, where here w of x, y is the probability of an edge between x and y, and we're integrating over the values dx and dy. And so when this integral evaluates to 0, we're going to get an empty graph. But when it's something that's positive, we're going to get asymptotically a constant times the number of vertices squared. And so this is easy to extend to an almost sure argument. And so we get that when we have a vertex exchangeable graph, it's always going to be dense or empty with probability 1. And so now we want to think about different types of graphs that can get us sparsity. And so I'm going to talk about our contribution of edge exchangeability. And so before we had a sequence of graphs where at each step a vertex entered. And so an alternative thing we might think about is now having edges enter at each step. So again, we're going to label the edges by the step that they enter the sequence. And so perhaps in the step 1, we have one edge coming in, and then the second edge comes in step 2, the third edge comes in at step 3, and the fourth edge comes in step 4. And again, what we're going to do is we're going to put a distribution on these graphs. And we say that it's edge exchangeable if this distribution is invariant to permutations of the order of these edges. So once again, here we can see that the edge that came in step 1 is now in step 2. So now that I've defined what it means for a graph to be edge exchangeable, what we're going to do is we're going to find a Di-Finetti mixing measure for this. And the way we're going to do this is, first I'm going to take a brief detour, and I'm going to talk about random partitions and clustering. And this is going to help us figure out how to construct such a what we call the graph paint box, such a Di-Finetti mixing measure for edge exchangeable graphs. So in clustering, we have a bunch of data points, and what we'd like to do is some unsupervised learning process where maybe there are these latent clusters that we want to learn, and perhaps we have a bunch of images of animals that we'd like to ideally infer some sort of cluster that refers to the animal, such as the cat cluster or the dog cluster. We say this clustering is exchangeable if, when we permute the data points, it doesn't change the distribution of our random partition. So now I'm going to tell you a way we can generate a random partition, an exchangeable random partition. So let this represent the unit interval, and suppose we have this realization of a random partition of the unit interval. So notice here we have a bunch of intervals whose union is 1, and so the sum of their lengths is 1. And they also are mutually exclusive in that they don't overlap. And so the way we can draw an exchangeable clustering from this is by drawing these IID uniform random variables over the unit interval, and then letting the color in which it lands in represent the cluster it belongs to. So suppose the first data point lands here, and the second data point lands here. So you notice that both of these uniform random variables are falling in the same interval, and so they both belong to the blue cluster. And the third data point might land here in a different color interval, and so what this corresponds is this data point is now going to belong to a new cluster. And so we can keep doing this process, and here we've sort of generated this partition of our data. And in fact, this clustering is exchangeable because if we were to permute any two of these data points, it amounts to permuting these IID uniform random variables, and so this won't change the distribution of our random partition. And so what Kingman showed was the other direction of this. So now we have this construction where we can sample this exchangeable partition, and Kingman showed that, in fact, for any exchangeable random partition, there exists such a Kingman paint box representation. So now that I've introduced this paint box, we want to think about how we might generalize this for graphs. So maybe once again in our animal analogy, these colors represent the cat and dog and so on clusters. And so visually we might imagine pulling these intervals down. And so it's still a random partition in that these pieces are non-overlapping and their weights sum to 1. So a way we might generalize this is sort of relaxing the assumptions of it being mutually exclusive and exhaustive. So here's an example. Now we can see that there are overlapping pieces of the unit interval, and if we also have parts that don't cover the entire unit interval. So it's no longer mutually exclusive because it's overlapping and it's not exhaustive. And so also for graphs, we might now think of these horizontal slices. This is a union of subsets of the unit interval, and they can the total length might correspond to say like the probability or some likelihood of these vertices connecting to other vertices in the graph. So we're going to call this like the cat vertex, the dog vertex, the mouse vertex, and so on. So now that I've presented this construction, I'm going to tell you how you can sample an edge-exchangeable random graph from it. So once again, we're going to sample these IID uniform random variables. And draws represent edges because an edge sort of connects two vertices. So here we can see if the first data point lands on this yellow and red subset, that's going to form an edge between the cat and the mouse. And so in our second step of the sequence, we might not hit any of these subsets. And so this amounts to not drawing any edges. In our third step, we might only hit a single subset, or the yellow one, which is the cat vertex, and that corresponds to a self-edge. And then we might not hit anything again in step 4. And then in step 5, we might get a new one hitting the cat and dog vertices, and so we draw an edge between cat and dog. Step 6, so this is sort of a new case where now we're forming an edge between lizard and sheep, which is this green and yellow subset. And this sort of forms an edge between two vertices that haven't previously participated in the graph. And it's not connected, this edge isn't connected to any other parts of the graph. We can also have a type of edge which already occurred previously. And so now, step 7, we're once again hitting the blue and yellow subsets. And so this forms a graph with multiplicity. And this graph is, in fact, edge-exchangeable because when we permute two of these steps, and these steps correspond to edges, we're permuting these two IID uniform random variables, and so it won't change the distribution of our graph.
Can you have more than 2?
Yes. So, in fact, that would correspond to a hypergraph. So what we're able to show is that, in fact, for any edge-exchangeable graph, there exists such a graph pink box representation. And so this pink box construction that I've presented is the Di-Finetti mixing measure for edge-exchangeable graphs. And also, as I just mentioned, this generalizes to hypergraphs, where now instead of 2 overlapping pieces, we just need a finite number. OK, so now I'm going to talk about a specific subclass of edge-exchangeable graphs, and we sort of call this the graph frequency model. And then within that, I'm going to talk about another subclass that exhibits sparsity. And so this is sort of meant to just show that there exists a class of sparse graphs that is edge-exchangeable. So suppose all of the total lengths of these subintervals are proportional to these values, W1, W2, W3, and so on. We can construct this special type of pink box where now we require at any sort of vertical slice there's exactly 2 overlapping subsets. And what this corresponds to is when we draw an edge, it's always going to connect 2 vertices, so we don't get any self-edges and we don't get no edges. Furthermore, if we look at the overlapping parts of any 2 subsets, the lengths of these are going to be proportional to, in this case, W1 and W2, but more generally, Wi and Wj, where I represents the weight of vertex I and j is the weight of vertex j. So now we can think about this as a frequency model where we've sort of collected all of these weights, and we're going to suppose that we have this infinite collection of these weights. And suppose that the weights are generated from a Poisson process, where the rate measure of this Poisson process has power law tails. So in our work, we've shown that under these conditions, and we have that the growth of the number of edges is going to be subquadratic in the number of vertices with probability 1. And so this sort of accomplishes our goal of showing that we can get sparse graphs under edge exchangeability, which we couldn't get in the vertex exchangeable case. So this type of frequency model that I just described is very much inspired by work by Caron and Fox and Veitch and Roy. And here's sort of like a cartoon that, if you can see, we're assuming that we have this, once we draw our weights, we fix our weights, and then we draw edges on top of that. Whereas in the Caron-Fox setting, they have this interval and this parameter that they're sort of growing to add new vertices to the network, and that corresponds to sort of instantiating this latent infinity of weights. Okay. So now I'm going to talk about a specific family of models. This is when the weights are generated from a 3-parameter beta process, and that's just like a Poisson process where we've chosen a specific rate measure of a specific form. And if you're familiar with beta processes, the 3-parameter beta process just has this extra parameter that's called the discount parameter, and so when it's equal to 0, we actually get the 2-parameter version. And so the weights are generated from this 3-parameter beta process. Oh, and then the alpha parameter, it sort of controls the decay of our weights as well. So we draw our weights, and then for each vertex, I and j, we're going to independently flip n edges with probability wi times wj. So this will generate a multigraph. And so in our work, we've seen that when we have the 3BP, we actually get sparse power laws in graphs. In fact, we get a range of sparse and dense power laws. And so I'm just going to show some simulations of our using the 3-beta process. And we looked at 2 types of graphs. The first is a multigraph, which is just generated from the model. And then the second is this binary graph, where we've taken any edges with multiplicity greater than 1 and restricted them down to 1. So what I did was we took so for that the n value that we were flipping all of these edges for any pair of vertices, I made that go to something large, and I plotted the number of vertices against the number of edges. And here, if you remember, vertices are instantiated by edges. So a vertex here, we're only counting the ones that participate in some edge. And so this is plotted on a log-log scale, so you can see that all of these plots, they have this linear relationship, and the dotted line represents a line of slope 2. So we can see that, so in our theoretical results, we showed that when alpha is greater than 0.5, we get sparsity. And so that's for the more general class of models that I described earlier. And here we see that our simulations match up with this, in that in the multigraph case, we can see the slopes of the second row, alpha equals 0.6 and 0.7, that they're below 2. And whereas in this first row, we have alpha equals 0 and 0.3, and you can see that their slopes are greater than 2. So in the binary case, in the more general class of Poisson process models, we showed that when alpha is greater than 0, we get sparsity. And when alpha is equal to 0, this actually is the 2-parameter beta process. And so once again, we get this range of sparse and dense power laws. And so here we can see that when alpha equals 0, the slope is greater than 2, so this is not sparse. Whereas in these other parameter settings of alpha greater than 0, we have a slope that's less than 2. And so now we get sparse behavior. And so our simulations sort of verify and match up with our theoretical results. All right, so I've presented a problem. It's that vertex exchangeable graph models are dense. And so there's this whole set of these popular graph models that make this assumption, and therefore can only generate these dense graphs. And that's too many edges for what we consider to be realistic in graph modeling. And so I presented a solution, which is using edge exchangeability to build models that can get us sparsity and power laws. And to recap, first I defined what it means for a graph to be edge exchangeable. And if you think of this circle as the class of edge exchangeable models, what we then did is we gave a Deep-Inetti style characterization, which we called the graph paint box. And this characterizes the distribution of these edge exchangeable graphs. Next, I showed that under this assumption, under edge exchangeability, we can actually get sparse graphs. And we did this in 2 steps. First, I introduced this type of graph frequency model, where we're looking at sort of the product of these weights for the probability of an edge between I and j. And then I looked at a specific subclass and showed that that subclass can indeed get us sparse graphs. Lastly, I looked at the 3-parameter beta process, and we just saw some simulations where we can get power law behavior, and in fact, a range of sparse and dense power law behavior. So in this talk, I just sort of talked about how we can get sparsity and that there exists a class of sparse graphs when they're edge exchangeable. But what we'd actually like to do in future work is actually characterize this class of sparse exchangeable, edge-exchangeable graphs. Another direction we've been thinking about is looking at different types of power laws and characterizing them. So in this talk, if you recall, I only talked about one type of power law, and it's power law between the vertices and the number of edges. And so we might also consider other power laws, for example, in the number of vertices and the number of triangles, or a power law in the degree distribution. Another thing we've been thinking about are probability functions that characterize the distribution, and they're a function of just sort of various graph quantities, such as perhaps the degree or edge multiplicities. And this is sort of analogous to this idea of exchangeable partition probability functions in random partitions. Another thing that we're really interested in is actually building real models for data and doing inference. And so if you remember, we talked about this graph frequency model, and one of our original motivations for this work was thinking that it might be sort of amenable to doing these truncation approximations where we truncate the infinite tail of our random measure. And this sort of goes well with a lot of this vast body of work of inference that we've seen, such as variational inference or Hamiltonian Monte Carlo methods. And so this is something we're looking at exploring next. Okay, so our work is currently under submission, but you can read about it online. It appeared in these NIPS 2015 workshops on networks and also Bayesian nonparametrics. And I'll also point you to this concurrent work by Harry Crane and Walter Dempsey on edge exchangeability for graphs and network data. And then here are just some additional references that I talked about in the talk. All right, thank you.
So in your paint box model, of course, it's important how big the measures are of the different sets for the different groups, but also how large the intersections are. Mm-hmm. So I didn't understand in your random model when you sample the WIs according to some distribution, but how do you decide how large the overlaps are?
Well, that sort of depends on the model. So here we looked at this. The only case that we specifically looked at is this graph frequency model where the overlaps are proportional to the product of the weights.
I see, so instant independent, yes. So I guess you've thought more about this. I get the impression that this model, if you take the case now with only graphs, no hyper edges and so on, that this is essentially equivalent to the model that Harry Crane talked about the other day. His frequencies Fij will just correspond to the measures of these intersections of the ith and j sets.
Yes, I believe that's correct.
Mm-hmm. Yes. But then you have another feature that you can also get hypergraphs. So this also means that this would be a way, if you think of a triangle not as a hyperedge but as three separate edges, it would give you another way to generate random graphs with lots of triangles, for example, which you will not get easily in other modes of sparse random graphs.
All right, yeah, that's a good point.
Yeah.
Yeah. So you mentioned in the beginning that there's Harry has a very comprehensive set of results on this, and but you mentioned that there are some differences. Maybe can you briefly highlight for us what the differences are? I suppose that's specifically the beta process model.
Yeah. So I guess so. I mean, my understanding is, and this is also different than some of the earlier work I presented on this. But in this sort of paint box representation, previously we had thought about paint boxes where essentially we had probabilities corresponding to edges, whereas now they correspond to vertices. So that sort of allows us to model edges that contain, for example, the same vertex, and sort of get this additional information about vertices. I think with regard to the results, we were looking at this class of sort of completely random measures which has this certain power law tail for the Levy measure. And so that sort of gives us this large class of potentially...
That should be in the three-parameter beta, stable beta process, right?
Well, so our results are for more generally than the beta process, the 3BP. It's just for when we have certain assumptions on the decay of our weights. And then it's just in the 3-parameter beta process, we looked at simulations, and that's sort of the specific case where we were just able to see that our simulations matched up with our theoretical results for the more general class.
Yeah, so I wondered if the ordering matters and the ways, because if you take the biggest one and flip it to the bottom, then you might not show as often because it might cross two other, because you stop, like in a regular graph setting, you stop at the biggest, the two overlaps, right? In that sense. So does the ordering of the weights matter?
I mean, what the draws are just intersecting the vertical slices.
Yeah.
So, and they're IID uniform, so the way it's like ordered shouldn't matter. That answers what you're thinking.
So, Svante is here, right? So, about the representation, so I only showed the one with the Fij's, but we have one for hypergraphs.
Okay.
But about this representation here, Dan Roy mentioned there's an aspect of his representation which allows for these isolated edges and isolated stars. And we also have that from our representation, but I don't see how that would come about in this from here.
Right, so here I'm sort of like ignoring those special cases. So it's just sort of ruling out any sort of like dust for like single edges, or singleton edges.
So I guess in what sense is it a characterization?
I mean, it's sort of when we make the assumption that we're not looking at graphs with those extra structure. And so we can only get this sort of regular set of graphs.
Also, if I could just say, so you have the possibility of, at a given time, not seeing anything, right, in this representation. So if you observed a graph with, say, 5 edges, you don't, I mean, what's the sample size? Because you could have had a bunch of, in principle, according to your model, empty observations. So how do you know what you're allowed to label the edges by and what the marginal distribution should be?
Well, so I mean, we allow for not having any edges because it's sort of, if we were to write it out in the sequence and we might not observe a new edge in that sequence, and so in that case, that we allow for that, but we're more generally discussing the case where we only actually draw an edge at every sequence. Because I think under the more general case, we don't actually care if it was a specifically new edge added at this sequence, as long as when we were to permute the ones that we did observe, it doesn't change any of the distributions. So in our actual model, we do look at the case where we are getting an edge in every sequence.
When you talked about sparse graphs, you gave as an example the number of edges grows as n to the power alpha, where alpha was strictly between 1 and 2. Mm-hmm. Can you get all the way down to alpha is 1 in this construction? So that the expected degree doesn't explode?
I don't think we've looked at that in particular. I think at least in simulations, we have been able to get close to that, but I'd have to look into it further.
I doubt it. I mean, I'm not sure. I may be wrong, but my guess is that it will always grow faster than linear, even if it may be arbitrarily slowly faster.
Okay.
Yeah. Okay.
Is that again?